Hi, everyone. My name is Dr. Noelle Cutter. I'm an associate professor at Malloy College in the biology, chemistry, and environmental science program. Today, I'm going to talk to you about science and communication and my life as a science advocate. And I think this topic is extremely relevant given the current state of affairs with the COVID-19 pandemic. So I still remember about a year ago, maybe a little bit more than a year ago, talking about this strange new virus that was reported in Wuhan, China. Little did we know how bad things would get. In March, it really felt like we began a free fall into a period of uncertainty, isolation, and fear. It is now a year later, and looking ahead to the spring, I'm going to be honest, I think we still have a bumpy ride ahead. There are still hundreds of thousands of people that are going to be tragically affected by this virus. They're going to get sick, and some people may die. But at the same time, I'd like to offer a glimmer of hope. In the last few months, we've seen millions of people across the globe become vaccinated against the coronavirus. And hopefully now we can really begin to change the trajectory of this virus. The COVID-19 pandemic is caused by the SARS-CoV-2 virus and has really resulted in an unprecedented public health emergency. The pandemic has afflicted more than 170 million people across the globe, and it has resulted in over 2.7 million deaths, according to the World Health Organization. The etiological agent of this pandemic is, of course, the newly emerging coronavirus, which causes severe acute respiratory syndrome, which we now refer to as the SARS-CoV-2 virus. So kind of battling this pandemic of misinformation, I thought it was really important to kind of talk about how the public kind of generally views scientific information. And really the rapid evolution of the COVID-19 pandemic has not permitted immediate and certain scientific data. I mean, we're really hot off the press at trying to understand what is going on with this virus. Substantial numbers of articles on COVID-19 have been published, yet there's still controversy among clinicians, confusion among the general population in this regard. Furthermore, it is really almost unreasonable to expect physicians, clinicians, healthcare experts to be able to read all of the current literature on the subject. So considering this, the need has greatly arisen, especially in the event of this emerging health crisis, that doctors really have to be able to provide the public with evidence-based information in a simple and shared way in order to avoid misinterpretation and misunderstanding. But of course, this is very, very challenging. We really need to see better coordination between the medical community, between governments, between the mass media, so that we avoid the spread of disinformation, misinformation, and we limit the dissemination of fake news and thereby make a better chance to really engage the general public so that we can follow the correct guidelines and we know what we should be doing and we can be safe and we can be transparent with our rules. And the rules need to really be guided by evidence-based discussions. And so this has been a really, really big challenge. And, especially, I personally, when I read news articles and when I read news headlines, sometimes I just go, oh my goodness, they've really misinterpreted the scientific data. And so as a scientist, it's been so important to really kind of share the right information without misleading the general public. And of course, that is a very challenging thing to do. So the global arrival of the coronavirus in 2019, the end of 2019, has brought really an increase in the number of manuscript submissions that are both describing as well as evaluating the spread of severe acute respiratory syndrome coronavirus 2, or the SARS-CoV-2, its infection, its morbidity, its mortality, distilling what seems to be like years of science and policy in only several months. And of course, that has been where a lot of this misinformation has come from. And so now we have to turn to the fact that compassion really pushes us to try and understand how we have structured this world and ask, how can we structure it better? Not because we may suffer, but because other people may suffer. And misinformation can really result in the suffering of other people. So, what is the coronavirus? What are coronaviruses in general? Coronavirus disease 2019, or COVID-19, is a disease that's caused by the newly emerging coronavirus, which is severe acute respiratory syndrome coronavirus 2, or SARS-CoV-2. Coronaviruses are a cause of the common cold. You get symptoms of the common cold, but SARS-CoV-2, which likely came from that, causes more severe diseases in many of its patients. It's spread primarily through respiratory droplets during close face-to-face contact or limited space contact, so people who are in close proximity to one another. Infection can be spread by asymptomatic, pre-symptomatic, as well as symptomatic carriers. So this has also been a source of contention as well as confusion. The average time of exposure to symptom onset is anywhere from 5 days. And we see about, on average, 97.5% of the people who develop symptoms do so within the first 11 to 12 days. The most common symptoms include fever, dry cough, as well as shortness of breath. SARS-CoV-2 itself is an RNA virus, so viruses can be RNA or DNA. And this means that its genome is just made up of RNA and not DNA. But functionally, what that means is that RNA viruses tend to have higher mutation rates than DNA viruses. And that's because the enzymes, like the polymerases that the viruses use to copy its genome, tend to make more mistakes when copying the genome. And those result, of course, in mutations. And we're going to talk about mutations when we look at some of the variants of the SARS-CoV-2 virus. And interestingly, what we have found is SARS-CoV-2, like other coronaviruses, are sort of a unique family in that they make fewer mistakes than other traditional RNA viruses might do. Because they have what's called a proofreading mechanism. They have proofreading enzymes that help to proofread their genomes. So they have proteins that are going to recognize mistakes and then can go back and correct them. So at the biochemical level, they make mutations less frequently than other SARS-2 viruses. So the first, hot topic that I thought I would talk about are vaccines. As we have seen, there's been a number of vaccines that have been authorized for emergency use authorization here in the United States. I'm only going to talk about the United States vaccines that have been authorized. So as COVID-19 vaccines are authorized and then recommended for use in the United States, it's been important to understand what we know about each vaccine. I feel that the CDC has done a pretty good job at providing information on who is and who is not recommended to receive each vaccine and what to expect after vaccination, as well as being very transparent about what the ingredients are, what the safety levels are for the vaccines, as well as their effectiveness. So currently, 3 vaccines have been authorized and recommended here in the United States. That's the Pfizer-BioNTech, the Moderna, as well as the Johnson & Johnson-Janssen vaccine. So the Pfizer and the Moderna vaccines were the first 2 that were authorized here in the United States. Those are based off of messenger RNA vaccine design. And the Johnson & Johnson vaccine is an adenovirus vaccine. So I'm going to talk about both of those. COVID-19 vaccines, the role of them, the goal of them, why we have them is just like any other vaccine. They're going to teach our immune systems how to recognize and fight the virus that causes COVID-19. Generally speaking, it takes about 2 weeks after vaccination for our body to really build full protection, full immunity against the virus. And so that's important to know, because this means that people who have been inoculated can still get sick and they can still pass COVID on to other people. until they're fully vaccinated, until they've really built up that full immunity. So the mRNA vaccines, which include the Pfizer and Moderna vaccines, are a new type of vaccine, but the technology for them has been around since the 1990s. So we've known about the technology for messenger RNA vaccines, but these are really new vaccines that have been designed to protect against infectious diseases, to trigger an immune response. Traditional vaccine development would use some sort of a weakened or an activated part of the virus that was injected into our bodies. But the messenger RNA vaccines instead uses a little tiny piece of the spike protein, which is part of the SARS-CoV-2 virus. And so with that tiny little piece of protein, that's going to trigger an immune response in our body. And that is going to allow our bodies to produce antibodies and protect us from getting infected should we come into contact with the real virus. The Johnson & Johnson COVID-19 vaccine is a single dose administration, whereas the messenger RNA vaccine for both the Pfizer and Moderna is a dual dose vaccination. So the Johnson & Johnson is a single dose administration, which makes it a little bit easier. And it is an experimental viral vector vaccine that uses a weakened live pathogen, the adenovirus, as its delivery, so kind of as its coat around a piece of the recombinant genetic material from the virus, which is again that spike protein. So it's going to still use a piece of the spike protein that's going to be coated in a viral vector, which is that adenovirus. And that DNA, that message for the spike protein can then be injected into our cells so that our cells can elicit a proper immune response. This genetic material for the COVID-19 does not replicate inside of our body. It only makes that tiny little piece of the spike protein that can be targeted. And this recombinant vaccine is very, very safe. It can be used in large populations of people, even those who have chronic health problems and who may be immunocompromised. And we're still, the jury's still out on whether or not we're going to need a booster shot. And that's also true for the messenger RNA vaccines. So again, this is a great little chart. I feel like this gives you a nice table of comparisons of the different vaccines. All in all, the ability of vaccines to prevent all infections may seem like our arcane topic compared to their proven ability to stave off moderate to severe illness and death. So that's really the bottom line at the end of all of this, is that we have to remember that these vaccines are safe, they're effective, they have been evaluated, and they do a really good job at preventing severe illness and death. And so, when we're talking about the effectiveness of the Pfizer and the Moderna, we're looking at 94 to 95% efficacious. And so that is out of their data that they have provided for us during their clinical trials. And so kind of thinking about this and these COVID-19 vaccines, we're still kind of learning about them, and we're still kind of learning about the likelihood of transmission, especially within asymptomatic populations. But so far, it seems that in general, the population, we've seen a reduced effect of transmission when people become vaccinated. And these vaccines work really, really well. And so we're very thankful to have them and to be able to prevent really severe illness and death in populations of people. As far as glimmers of hope and the role of reducing transmission, of course, this has been a big question. And so the biggest lingering question right now of the pandemic is, do these COVID-19 vaccines reduce transmission? And it's important to keep in mind that not all vaccines are designed to do so. These vaccines were designed with the end point in mind of reducing severe illness and reducing hospitalizations and reducing death. So it's important to figure out So we know what we can and cannot do, like when can we stop wearing masks? When can we start hugging grandma again? When can we visit non-vaccinated people? And so this slide here just gives you some early indications of glimmers of hope in that idea of reduced transmission. So there was a couple of studies done after the Pfizer trials that have shown reduction in asymptomatic infection by as much as 89.4%. So again, these are more observational studies and not clinical trials, but the data is really, really great. A lot of the data is coming out of Israel because they've done an excellent job at rolling out their vaccine, and they have a large percentage of their population who have become vaccinated for COVID-19. There's also a paper that was published in The Lancet that has shown up to a 75% reduction in asymptomatic COVID-19 cases as detected through their general testing platforms. As far as the Moderna vaccine, there's also indication that the Moderna vaccine has shown reduction in asymptomatic cases as well. So right now, overall, I would say it's looking pretty good that we've seen reduction of transmission, and that we'll be able to start kind of opening up our country a little bit more. So in summary, although COVID-19 vaccines are very effective at keeping you from getting sick, scientists are still, we still have to learn, we're still collecting the data on how well these vaccines are going to prevent you from spreading the virus to others, especially if you're not showing symptoms. So right, the asymptomatic transmission is a big question. Early data, as indicated in the slide before, do show that the vaccines help to keep people with asymptomatic transmission from spreading COVID-19, but we're still learning more. As more people get vaccinated, we're still going to get more observational data, and that we'll be able to kind of answer this question a little bit with a little bit more clarity. We're also still learning how long the COVID-19 vaccine will protect people. So that's another big question. How long will we have protection to this virus? How long will that antibody and that immune response last? For these reasons, people who have been fully vaccinated against COVID-19 should keep this message in mind. And you really want to make sure that you're taking the necessary precautions in public places until we know more. So things like wearing a mask, staying 6 feet apart, avoiding crowded places, avoiding poorly ventilated spaces, and washing your hands often. But all in all, we've seen that the COVID-19 vaccine does give us immunity. It does help to eliminate the virus. Most importantly, it does prevent death. It doesn't guarantee that you won't get it, but if you do get it, the chances are it's going to be much more mild. It does stop you in at least 70% of the time from passing it on to others. It will eventually start to lift some of those travel bans. It will eventually allow businesses to start opening up again. It will eventually, to end the need for having lockdowns, and it will eventually eliminate the need for masking. But while we're still getting our population vaccinated, it's still important that we follow these guidelines. And so that kind of brings us to the next question of herd immunity. What is herd immunity? Thinking traditionally about what that term herd immunity means, scientists initially estimated anywhere on the order of about 60 to 70%. I think it was like 66.6%. 2 out of 3 individuals in the population are going to be needed to acquire resistance to the coronavirus to banish it. But as we've heard, standards across the United States in particular, Dr. Anthony Fauci and others have been kind of quietly shifting this number upward, and that's totally okay. And the real reason is because we really don't know how many people that we're going to need to have protected in order to prevent transmission. So this goes back again to that asymptomatic pre-symptomatic, symptomatic transmission question, vaccination versus non-vaccination. So what portion of the population must acquire resistance to the coronavirus, either through infection itself or through vaccination, in order for the disease to fade away and for life to return to normal? So this is kind of like, we really don't have the answer to this question. So since the start of the pandemic, many epidemiologists have suggested anywhere from 60 to 70%. And that range is still cited by many organizations, such as the World Health Organization, and is often repeated during discussions of the future course of the disease. So although it is impossible to know with full certainty what the limit will be until we reach it, until transmission stops, right? Until we have the data collected to understand that transmission of the coronavirus has stopped. We really don't, we can only give good estimates. But having this estimate is going to give Americans a sense of when we can hope to kind of breathe a sigh of release again. So recently, we've kind of been shifting that goalpost up, especially as we switched in the administration policy from the Trump policy to the Biden policy, to the Biden administration. So we've been raising this herd immunity estimate, and we really don't know what the real number is going to be. I think the real range is going to be anywhere from 70 to 90%, but I think it's better to say 90% so that we can continue to get populations of people vaccinated. And the more people we have vaccinated, then the closer to herd immunity that we're going to see. I don't think we have to reach a point where we get to that R0 zero transmission value in order to have a decent society. We have lots of diseases that circulate in our populations, things like the flu, that are being transmitted all of the time, and we don't have to shut down society for that. So if we can vaccinate almost all of the people who are at the most risk of severe outcome, then this would become a much more mild disease. This might become something more manageable, where we're not really shutting down our entire society to deal with it. So when will we reach herd immunity? I think this is a really difficult question to answer. Herd immunity in the next couple of weeks, of course, sounds really wonderful, but it's important to keep realistic expectations, which I think scientists are better at doing. So I'm pretty doubtful that this is ever going to happen. But if reaching herd immunity and, that idea of when we end this pandemic hinges on kind of three main factors. The first one is the amount of protection from natural infection. So people who have been infected with SARS-CoV-2, which we are still trying to figure out. So get your vaccine, even if you've had COVID-19. Two, we need to convince people that the vaccine is safe, that the vaccine is effective, and that the only step, and that really this is a major step towards herd immunity. And finally, the third caveat to this rule of herd immunity is the impact that some of these new variants are going to have on herd immunity threshold. Based on today's post kind of reaching 70 to 90% estimate, especially with these new variants, I think that we may err closer to the 90% rule, but we're still trying to figure that out. And so that kind of brings me to my next discussion on variants. What are variants? What do we know about the variants? And of course, this is a lot of newly emerging data as it comes out. So what we do know, viruses mutate. They're mutating all the time. And so the appearance of mutants of COVID-19 really shouldn't surprise any of us. RNA viruses do tend to mutate more than DNA virus. And that's because we had already mentioned some of those proofreading enzymes are not available. Interestingly enough, SARS-CoV-2, like other coronaviruses, sort of a unique family trait is that they do tend to make fewer mistakes than other RNA viruses, because they have what's called these proofreading mechanisms in place. So they have proteins that recognize mistakes, and then they can go back and correct it. As mentioned before, they do tend to make less mistakes than other RNA viruses. But it's still challenging to understand and interpret that, because when you wake up and you read in the newspaper, and you're trying to understand how well the vaccines are working, and then you're hearing about all these new variants. So what's going on? What do we know about the variants? What do we not know about the variants? And how well will the vaccines work against some of these variants? We need to make sure that at the end of the day, that we're still using our mitigation strategies. So things like wearing masks, socially distancing, because we know that they work. And they're going to work against these variants as well. And the vaccines seem to be very effective as well against these variants. But at the end of the day, those original strategies that we have, those original measures that we have in place for masking and social distancing become super important, even after you've been vaccinated, and especially dealing with these variants. What is the impact of the effectiveness of the vaccines that, or the vaccines that we have, and the vaccines that are, coming down the pike, suggesting will these vaccines still work against some of these variants? And so far, the data suggests that, for example, the messenger RNA vaccines, the Moderna and the Pfizer vaccines, are working. They may not be as effective as their original 94 to 95% efficacious rate, but they are still working. Again, all of this data is observational, so it's unfolding before us in the population of people as they become vaccinated and as our population becomes exposed to a lot of these variants. So this is kind of this real world data status that we're in. For the Johnson & Johnson vaccines, again, those trials were run in South Africa when some of those variants were around, which may have, that would have reduced their efficacious amount. So they were about 70 to 75%, but they were run at a time when the variants were around. So again, there's some real world data that suggests that the Johnson & Johnson vaccine is also very effective at many of these variants. So for me, frankly, I think that what we need to do now is communicate with the general public, and really continue to be full steam ahead with vaccination. Right now, there's no reason to have any confidence that the variants are going to really impact the effectiveness of the vaccines. The vaccines are still working really well. So we really need to kind of keep moving forward with these vaccination efforts. But at the same time, we need to continue to do careful studies to evaluate the effectiveness of the vaccine and to see if these variants are really going to impact our vaccine recommendations. So we still really need to collect these data, this real-time data. When a new variant emerges and it's tested against, for example, the sera of someone who's been vaccinated, which is traditionally our way of understanding how well the vaccine is going to work against some of these variants, it shows us that it doesn't look like at this point that the virus has mutated far enough away from vaccination or from natural infection that you're going to be at risk for serious disease. So at the end of the day, that's where we are right now, and hopefully we'll stay there. So it's still working really well. Natural infection, vaccination have still been shown to be very effective against these variants. And so I think that we're going to continue to see variants emerge. This is going to be a continual battle, but we need to continue with our vaccination efforts. What you really want to do is keep people from getting severely sick, from ending up in the ICU, and to keep you from dying. And right now, the vaccines are effective at doing that. You're still producing this polyclonal antibody response against a variety of epitopes on that virus. And that response right now appears to be good enough to protect you from severe disease. So I think at the end of the day, that endpoint, that measure is the most important one. So this chart here just kind of outlines some of the variants that are circulating, some of them that have been in the headlines that you may have seen already. The B117 is the United Kingdom variant. was one of the early ones that have emerged. It carries a large number of mutations in the spike protein. It has since been detected in the United States as of the end of December. The B1351 South African variant. So that one is another one that has received a lot of headlines lately. Again, also has been found in the United States as of January. Preliminary evidence, though, does suggest that the Moderna and the Pfizer vaccine are effective against this variant. But again, further evaluations are going to be absolutely necessary. The B1351 South African variant also has a number of mutations in that spike protein. The P1 variant, so this was one that was a new variant of concern. This is the one that was found in, first detected in Japan as well as Brazil. And it was first identified in January 2021 in travelers from Brazil who then arrived in Japan. It was detected in the United States towards the end of January, I believe. This one has 17 unique mutations, including 3 in the receptor binding domain of that spike protein, which is how it attaches to the receptors in our own cells. The jury's still kind of out on the ability of this variant to spread more quickly than the natural wild type virus that first emerged last year. There is also some supporting evidence, the epidemiology studies that have shown that variants with this specific mutation does spread more quickly than variants without this mutation. It is a variant of concern, one that we are keeping an eye on. But again, the vaccine does still seem to be effective. Even if it has reduced effectiveness, it's still effective at really causing severe illness and people dying, which again, at the end of the day, is the most important measure. There's a number of other variants of concern that are emerging. We have a lot of early non-peer-reviewed studies that suggest that some of these other variants of concern might have greater effect on different populations of people, such as elderly populations of people, that might be contributing to longer stays in the ICU, might be contributing to more transmissibility. So we're kind of still studying the overall patterns of mutations and trying to understand some of these more newer variants as they arise within our population. So bottom line is we need a heck of a lot more data on transmission, on vaccine efficacy, and disease progression moving forward. So I have all the hope of our scientists doing a great job there at trying to understand these variants and to continue to collect data on them. Another hot button topic, of course, during with COVID-19 is pregnancy and COVID-19. So for the most part, many questions still remain. Researchers really want to know how widespread COVID-19 infection is among pregnant women overall, because the majority of the data collected from women who end up in the hospital for any reason during their pregnancy is going to help to contribute to our knowledge of what we know about pregnancy and COVID-19. Scientists are also studying whether women are more vulnerable to getting a viral infection when they're pregnant, or is it during some particular phase of pregnancy that they might be more susceptible, or is it during postpartum recovery? So we're still trying to understand the impact of pregnancy and COVID-19 and what that means for women when they're pregnant. But some of the early data that we do have suggest, so first of all, we have no evidence to support that the vaccine interferes in any way with fertility or with pregnancy. One of the concerns that first arose, that was kind of, one of those misinformation that was all over social media at some point, was looking at a protein called synectin-1, which shares similar genetic instructions with part of the spike, part of the spike protein for the coronavirus. The same protein is an important component of the placenta in mammals. So if women were getting a vaccine that causes the body to make antibodies against Senectin-1, which was similar to the spike protein, this news report was arguing that it may also cause the body to attack and reject the protein in the human placenta, making women infertile, making women more susceptible to losing the baby. And of course, this was picked up by a number of different websites and social media sites. A lot of this misinformation was spread. And so what's important to know is that the coronavirus spike protein and the Senectin-1 do share small stretches of the same genetic code, but certainly not enough to make them a match. It would be like two people having a phone number that both contain the number 7 in it. There's one tiny little connection, but they're not exactly the same thing at all. So you couldn't dial one number to reach the other person, even though their phone number shared the same digit, right? So that's important to note, that they were similar on a very, very tiny level. And we've looked at some of the data already. And so indeed, data from human studies of the Pfizer vaccine don't bear out this theory. In the Pfizer trial, which included more than 37,000 people, women were given pregnancy tests before they were accepted into the study. They were excluded if they were pregnant. And that's something that's up for contention. Should we include women who are pregnant in trials going forward? So that's a bioethical question to ask now. But during the trial, 23 women did conceive, likely by accident, and 12 of these pregnancies happened in the vaccine group and 11 in the placebo group, and they continue to be followed throughout their studies. There's no evidence to suggest that the vaccine is going to affect pregnancy. And in fact, the ACOG highly recommends that women get vaccinated because becoming infected with COVID-19 during pregnancy can have much more dire effects. And so that's what this slide is all about, the risks in pregnancy. And this is looking at registries and research worldwide on women who tested positive for the new coronavirus while pregnant, suggests that women overall with COVID-19 are a much higher risk for hospitalization as well as severe disease than women who are of the same age and not pregnant. So this report was published in Nature. But the good news is that risk to the unborn baby, to the fetus, is very minimal. And for the most part, they're mostly spared from severe respiratory infection, and they often do not even get sick. So it appears that the virus only rarely crosses from the mother to the fetus. And, this graphic kind of just compares the outcomes of intensive care admission and preterm birth for pregnant women with and without COVID-19 across a total of 77 different studies. There's still a lot left on this topic that researchers really want to study and understand, and to try to figure out whether a mom's immunity can be passed to the baby. And some early studies suggest that this is the actual case. So that's some good news coming out of some early data. Another misinformation is the origin of this virus. And so there was some question originally, did this virus escape from a lab in Wuhan, China that was studying it? Just to throw it out there, that most scientists pretty much agree that the virus that causes COVID-19, SARS-CoV-2, came from bats, and that these bats were inside of China. And, that the idea that COVID-19 emerged from a lab is highly unlikely. And it's much more likely that the bats kind of had an intermediate host, and then that jumped from the intermediate host into humans. And, early data suggests that this is probably the case, and that it was not created in a lab. And it's almost improbable that it was generated in a lab altogether. It is more probable that the virus resulted from some form of natural selection and the changing of the host animal before the zoonotic transfer into humans. And we can base that off of the similarity of the SARS-CoV-2 to the bat SARS-CoV like coronavirus 2. And so that was likely the reservoir for the original virus. It is important to note that advances are still needed to come to a better understanding of virus origins, most notably the ability to accurately infer deep evolutionary history from the phylogenetic analysis of the conserved protein structures. But looking at the structural detail of the conserved protein structures, it is highly unlikely that the origin of the virus was something that was manipulated in a lab. And so sequence homology to other coronaviruses and in other species shows that is unlikely. Okay. What about dietary supplements and its effectiveness against the SARS-CoV-2? So there's lots of people who tout about dietary supplements in the treatment and prevention of coronavirus. Evidence evaluating these supplements in patients is really lacking. So providers and patients should really not rely on dietary supplements at all to prevent or treat COVID-19. But it's more important that we rely on evidence-based guidelines to guide treatment decisions. So the bottom line is conclusive evidence from high-quality clinical trials is severely lacking, and data addressing supplement role with COVID-19 are absent. So the current guidelines do not recommend or even comment on dietary supplements. And, it is widely lacking in clinical trials. So there's really no self-treatment options. And a lot of times patients are still going to go out there and they're still going to try and self-treat with supplements. And so it's important that those decisions be guided under a healthcare guidance. And we have to remember at the end of the day, the best method to prevent the spread of COVID-19 is to avoid being exposed and to getting vaccinated once your chance opens up. And, that we have really no evidence to support the role of dietary supplements in the prevention and treatment of COVID-19. There was an interesting paper that had come out back in April 2020 that showed a link of blood type and its influence on coronaviruses. So geneticists have turned up intriguing links between DNA and disease in general. This paper looked at a connection with patients with blood type A that seemed to be at a greater risk for increased risk of respiratory failure with COVID-19. And this looked specifically at one of the genetic spots within that blood type A. And so having blood type A was linked to about a 50% increase in the likelihood that a patient would need to get oxygen or to go on a ventilator, according to this study. So that was just an interesting study looking at the genetics on chromosome 3, a gene cluster on chromosome 3 that showed a connection with a greater likelihood of severity of disease in coronaviruses. There's a lot of emerging data on the safe return to school. I'm not going to spend too much time talking about it, but the idea that transmission in school is certainly possible, and we need a whole lot more data, especially in some of our upper level students in high school and in higher education where I work, to make more policy decisions. But the kind of the glimpse of what's going on with school transmission. What does the science say? So there's evidence that suggests that K-12 in-person school attendance is really not a primary driver of community transmission. So we do know that children can become infected with SARS-CoV-2. They can get sick with COVID-19, they can spread the virus to all of that we do know. But evidence indicates that children in general are less susceptible than adults, and they also may be less infectious. In addition, children are less likely than adults to have severe illness or die and are more likely to be asymptomatic. So evidence from the studies that we do have suggests that the risk for SARS-CoV-2 introduction as well as transmission among elementary school age children might be lower than that for example, middle schools and high schools. As a result, evidence suggests, and this is where those evidence-based decisions need to come into place, evidence suggests that a need to adjust mitigation strategies based on higher susceptibility and infectiousness among teens compared to those of younger children is certainly warranted. Data suggests that it's possible for communities to bring down cases of COVID-19 while keeping schools open to in-person instruction. Furthermore, models of consistent implementation of mitigation measures in schools have shown success in limiting outbreaks and infections in school. The CDC does provide lots of guidelines on how to open up schools, what strategies are necessary to keep children as well as teachers and staff safe, and to kind of reduce transmission in the schools. Personally, I really think that it is critical for schools to open and remain open for in-person instruction. I also think that at the end of the day, the safety of it is the most important measure. It's critical for schools to open as safely and as quickly as possible for in-person learning. We really need to enable schools to open and remain open when they can really implement the proper actions to slow the spread of SARS-CoV-2 and not only within the school, but within the community as well. And so this means that students, families, teachers, staff, all community members really need to make sure that they're taking actions to protect themselves and others where they live, where they work, where they learn, where they play. So that, in short, success in preventing the introduction and subsequent transmission of SARS-CoV-2 in schools is going to be connected and dependent upon preventing transmission in communities. So the two are going to have to go hand in hand. And so where do we go from here? As we kind of surpass a full year of this pandemic, one thing remains clear. We really need to begin to rebuild our nation, our public health system, and we really need to instill some level of confidence to those that it serves. Only half of Americans trust the federal government to combat COVID-19, according to many of the recent polls. The importance of building trust and leadership in the work of our nation's world-class scientists and researchers, and is really a big goal and a big mission for public health. And that continues to be important as we move forward. Building trust is going to be vital to ending this pandemic, as well as future efforts to promote health and control diseases, because it's likely that this is not going to be the last public health emergency that we face. To do this, each agency must commit to be honest, to be consistent with their communication to the public, that articulates the latest science and takes a transparent, evidence-based approach to accelerate the nation's response to this pandemic. So how do we begin to rebuild our nation after this public health emergency? No single event since the end of World War II has really affected the lives of virtually every person living in every country of this world. The current state of the pandemic has offered a chance for scientists to speak science, to educate our community, our friends, family, and even our school children. I know for me personally, I have helped coach educators, healthcare workers, lawyers, politicians, as well as my own children who are elementary age. I've played an instrumental role in the science advocacy on Long Island as being a citizen scientist and giving a chance to teach and provide evidence-based approaches, help people understand where they can go to look for answers, and also give a level of transparency as well as compassion about sharing accurate information. Surely right now, this moment calls for us to all carefully reflect, as well as reinvest in compassion as a foundational approach to health. We really need to call attention to compassion in this way, and to point out the tangible good without which health for all becomes impossible. This kind of, in a sense, COVID-19 has really shown us that being a healthy person as well as living in a healthy world are going to be two of the same things. Healthy people and a healthy world are both strengthened immeasurably by having compassion at the heart of health. And so I end my talk today as being a science advocate and just letting you know that we really need to instill our trust back in science and understand that evidence-based approaches are going to be really helpful for not only this pandemic, but also future health emergencies. And with that, I'll be happy to take any questions that you may have.